Okay, can you hear me?
Oh, yes.
Thanks. Okay. So, let me start. First of all, someone asked me yesterday whether it is possible to attend the examination, of course online, the online examination, but using a room at the university, okay? I couldn't understand whether you mean a room with the PCs already, or just a room just to exploit the quality of the Wi-Fi, of the connection, but you're going to use your laptop. I think that there is a possibility to have a room with the necessary PCs on the desk, okay? Because I guess that not all of you may have a laptop for that. So my choice is, I think it will be possible. This is the important message. But we have to decide whether to use a room with PCs, okay, already, and a room or a room like this, because you are going to bring your own laptop.
Yeah, Professor Armandini was having the same doubt. The problem is that maybe if we connect with the university Wi-Fi, maybe there may be some connection issues with our own laptops. I mean, generally Wi-Fi's in university areas are quite slow.
Are quite strong?
Slow,
huh?
I mean, that's my... so maybe some computers of the university have a stronger connection, and we might not have errors.
Okay, so let's do this way. If possible, I will try to book a room with the PC already, and if one wants to use his or her own laptop, he or she can do that. Is that a nice set of alternatives? Okay. So let's do it this way, and I will let you know what is the rule. Another point is that if I don't know, at least approximately the number of people who are going to use the room, there may be issues, because it depends on the number of people, especially rooms with the PCs do not have many seats, many places, okay? So is there anyone who can at least approximately let me know how many people are going to exploit this possibility? And also, to avoid any issues, I think I will be in that room as well. But of course, you should keep in mind that this is not, I mean, I understand your point. I really would like that things start again to be in presence, because we all need that, okay? But you should keep in mind that this is an online examination. The only different thing is that you are in a room with a better Wi-Fi connection. So it's not a part of the room who are taking the examination in presence. This is an online examination, so you have to use your own sheets of paper, upload the result. For instance, you cannot give me a sheet of paper here. You have to upload them, okay? Because otherwise, it is like some people can take the examination in presence and other people cannot, which is not really good. Is that okay for you? So this is the first thing. And of course, also since some people in the chat, you can also do the examination from home, of course. Yeah, this is only for those who prefer to be here because they are not sure about the quality of their Wi-Fi connection at home. But I think that it is anyway an online examination. You can be at home, on the beach, or in the park, or any place provided that you have a Wi-Fi connection and there is nobody around you who suggests the solution of the exercises, okay? So you can stay at home if you like. And also, some people yesterday asked me also to provide details about the online examination. I will do that this week, and I will upload a file, which is, by the way, almost the same file I uploaded last year. So if you have access to last year's material, just look at the instructions because they are the same. And so I will upload one, the instructions for the online examination, in particular for the midterm exam, with some details about the time allowed and so on. And most important was another thing, and maybe I will remember later today. I will upload another thing which is about the instructions, but no, I can't remember now. Maybe during the lesson I will remember. Okay, so I want to continue with, these are examples of exercises that I regard as the very basics of what you should expect at the examination, at the written examination, okay? There will be also examples in 3 variables, even if I prefer in general examples in 2 variables, not because they are easier, because 3 variables is the same, I mean the solution is the same method, because they are, you can solve them faster, and so if the time is limited, it's better 2 variables than 3. Anyway, I will also show you examples in 2 variables, and you can adapt them to 2 variables and try to solve similar exercises in 2 variables. One is a maximum problem with a kind of function to be maximized, which is not strictly concave, but it has a part which is linear and a part which is concave. These kind of functions are very common, and they are called quasi-linear utility, quasi-linear objective functions, in particular utility. And in this case, we may have a constraint, which is an equality constraint, but also non-negativity constraints. Just remember one thing, we didn't consider explicitly the optimization with inequality constraints. But if you understand the part on equality constraints, you can understand a lot also on the part about inequality constraints without the need to explain the theory, specific theory about inequality constraints. This is one of the possible examples in which you can also add conclusions, considerations, if we have non-negativity constraints, even if, in principle, we don't know how to deal with them. But this is a very clear example. So if you have an objective to be maximized, which is like this, but you have also a linear constraint, so you have a quasi-linear objective function and a linear constraint, and additionally you have that your variables cannot be negative. What we do is, in general, what we do with this exercises is to neglect these additional constraints, just consider the equality constraints, solve the problem, and check whether your solution also satisfies the additional constraints. If this is the case, this is the optimal solution. If this is not the case, then we have to find some heuristics, some specific rule to find the optimal solution when these non-negativity constraints come into play, so they become really binding, okay? So they become really important for the solution. Is that clear? So what we can do in principle is to neglect these additional constraints. Another case in which this can happen is when we have here 1/2 x1 plus x2 less or equal to n. Just select the case equal to n, solve this case, and then try to understand what may change if we don't have less or equal to, but if we don't have equal, but we have less or equal to. So let me solve this one first, okay? And show you why this can become an issue. The solution can become an issue for what we know so far, okay? So I build the Lagrange function, 40 square root of x1 plus x2 plus multiplier times budget minus 1/2 x1 minus x2, which is exactly the same steps we follow usually. Partial derivative with respect to x1 is 40 divided by 2 square root of x1 minus 1/2 lambda equal to 0. And the solution, the derivative with respect to x2 is, since this part is linear, we have 1 minus lambda equal to 0. So, while the derivative with respect to x1 also depends on x1, the derivative with respect to x2 doesn't depend on the variables, okay? From this, I can immediately obtain lambda equal to 1. Then I replace lambda in the first equation, here. So it becomes 1/2 times 1. And this gives us the solution for x1. So the square root of x1 is equal to 40, means that x1 is equal to 1,600, okay? Very clear. But the point here, you remember the previous exercises with a function which was a multiplicative function and concave, strictly concave, like the Cobb-Douglas function, we here found optimal values of x1 and x2 that depended on n, because this is a parametric problem, okay? This is not specified. Here, the optimal value for x1 doesn't depend on n. So the optimal value for x1 doesn't depend on our budget in the optimal solution, and this may become an issue. So what is now the value for x2? Of course, since x1 has a unit cost of 1/2, if I use as a unit price of 1/2, if I consume 1,600 units of x1, I pay 800, okay? For that, the expenditure is 800, but the budget is m, so the budget which is left for the other good is m minus 800. And this comes out from the constraint here. So the problem is that if m is larger or equal to 800, I have a positive quantity or negative quantity for the consumption of x1 and a non-negative quantity for the consumption of x2. But if the budget is not enough, it is 700, for instance, I cannot provide the solution x2 equal to minus 100, because it doesn't make sense, okay? And also we have, these are consumption quantities, so we have no negativity constraints. So what would be the solution in the case where the budget is not enough? This is a common problem to this kind of problems with quasi-linear objective functions and linear constraints. Another example of a quasi-linear could be 40 times the log of 1 plus x1, for instance, okay? That would be concave in x1, but linear in x2. Okay, so the property of the solution here is that the other variable, the one which is not linear in the objective function, does not depend on the budget, okay? While the variable which is linear in the objective function appears linearly in the objective function is determined residually, provided that the budget is large enough. If the budget is not large enough, then the optimal solution will be, this is really common, it can be proven mathematically, but this is really common sense, okay? So you cannot consume 1,600 because you cannot consume minus something of the other good, okay? So you have to consume less of this. So the best thing you can do is not consume at all good 2, okay? x2 equal to 0. If x2 is equal to 0, x1 from the constraint is equal to 2n, okay? So basically, it is optimal, in this case, it is optimal to use all the budget to consume good 1 and consume 0 of the second good. Is that clear?
Is this a kind of assumption that we can effectively substitute the two goods?
The problem is substitution between the two goods. Okay, the problem is with this kind. Okay, this is the point. It was in the first slide. The utility. Let me spend a few words on this. Let me spend a few words on this. Of course, this is not. This is just a basic mathematics course. This is not a microeconomics course. But let me just give you the intuition of this. It's related to substitution between the two goods. Basically, it is related to the marginal rate of substitution between the two goods. If you have indifference curves, which are level curves, like this, they have a property. So this is the quantity consumed of good x, this is the quantity consumed y, let me say x1 and x2. x2 is the quantity consumed of good 2. And this is the combination, possible consumption combinations of the two goods, giving a specified, a predetermined level of utility, okay? So you can reach this satisfaction, this utility level, either by consuming a large amount of x1 and a small amount of x2, and a small amount of x1 and a large amount of x2. Also, the slope, you see that since this is convex, the slope here is almost vertical, then it is negative, of course, but then it declines in absolute value, and here it is almost horizontal, okay? This means that if you are already consuming very little of good 2, okay, and you want to consume even less, then you have to provide a large increase in the consumption of good 1, okay, and this becomes extreme at the extremes of this curve. If you consume this quantity of good 2 and you want to reduce it further, since also x2 is important for your utility, you have to offset this with a very large increase in the consumption of good 1, okay? And the same applies to the other branch of the curve. If you consume a very low quantity of x1 and you decrease this, you have to compensate with a large increase of x2. So there is a marginal rate of substitution, so the slope of this curve, slope of the indifference curve in microeconomics is called marginal rate of substitution between the two goods, and it captures this idea, and very typically it has this shape. The point is that if you have the level curves of this utility, if you try to represent these level curves of this utility, they are not like the previous one, okay? So they intersect, in this case, the x-axis. So this means that at this point, this particular property of the offsetting between the two goods doesn't hold. Okay, so it's strictly related to the marginal rate of substitution between the two goods. So the previous observations do not hold for these particular level curves. And this is why it is possible that at the optimal solution, one of the two goods must be consumed in quantity 0, which is not possible here. Look at this pictures. Okay, so here it is not possible because whatever the slope of the straight line that captures the budget constraint is, you always have a solution, whether the slope is very steep or it is very flat, you always have a solution that implies positive quantities consumed for both goods, which is not true here. And the graph is like this. Look at this. If the budget is low, the budget line is the green one, the dashed green one. If the budget is too low, if the budget is large enough, it is very likely that the tangency happens at a point that implies positive consumption quantities of the two goods. But if the budget is low, the tangency in principle might occur at the negative value of x2, okay? Which is not possible. So it can be shown that the optimal consumption in this case is this point on the axis, okay? Where I consume 0 of good 2 and a certain quantity of good 1. Is that clear? I mean, this is just what you should at least have the intuition of what happens here. Clearly, it is related to the slopes at the point where these indifference curves intersect the axis versus the slope of the budget constraint, okay? So geometrically, it is related to this relation between the two slopes. I don't want to provide the detailed formulas for the solution to be on the boundary or not, but the intuition is this. What you should know instead is how to solve the problem when it comes, when the budget is not large enough, okay? So in this case, you cannot consume all the quantity provided by your solution for good 1, for the good which is concave in the function. You have to consume less because you cannot consume a negative quantity of this. You have to consume 0, which is larger than a negative quantity. So you have to consume less than this. And the solution in this case is this one. By the way, the solution would change if the problem is one in which the linear term is x1. Okay, so for instance, you could try to solve this one, which is perfectly symmetric, just exchange the two, and call, and the objective function becomes 4t square root of x2 plus x1, subject to 1/2 x2 plus x1 equal to m. Try to solve this and to realize that now the problem is that you cannot consume all the quantity recommended for x star 2 because x star 1 would become negative in that case. So it's a useful exercise to try to solve also the problem that you obtain by just inverting x1 and x2 here. And of course, also here, you would have something that happens on this axis, where x1 is 0 and x2 is positive. So I hope that this is clear. Anyway, what we did basically is to solve the problem with an equality constraint and then just discuss the solution. Another interesting problem is this one, which I will comment later in connection with its with a strictly related problem, which is its dual problem. This is a problem in 3 variables, in which I have a linear function to be maximized and a constraint which is not linear. It is the sum of square roots. By the way, I hope that you realize what the trade-off is between the objective and the constraint. Without the objective, without the constraint, this problem, maximizing this function, is not a well-posed problem, okay? There is no combination of x1, x2, and x3 that maximizes this function. Because if I increase, since they all appear with positive coefficients, if I increase any of these variables, I obtain a value. This is actually, we have to minimize this, okay? But if I have maximize here, the same can be repeated for a minimum, but if I have max here and I don't have any constraint, okay, so I can assign to this x1, x2, x3 arbitrary large values, and I always increase my function, okay? So it has no solution, but if I add a constraint, of course, I cannot increase arbitrarily these variables, but only in a way that the value that I obtain here is equal to C, okay? Similarly, if I want to minimize this function, in principle, I could select the value 0, 0, 0 here, okay? Which is 0. So, assuming that I cannot select negative quantities, 0, 0, 0, but this is not this is a trivial problem, but if I introduce a constraint, I cannot reduce to 0 these variables because this function of the three variables must be equal to C, which is a positive quantity. So there is a trade-off between the constraint and the value to be maximized or minimized. It's like having two objectives, okay? It's like I'm interested in this objective and also this objective, okay? This must be large enough, and this must be reduced as much as possible. And this is like having two objectives, since in principle we cannot deal with multiple objectives in a simple mathematical form. There is a part of optimization which is multi-objective optimization, but it is something really different from this. Since I cannot deal with multiple objectives, usually I select one objective and the others are expressed as constraints, okay? Okay, this is an objective, you want to minimize this, but keep in mind that this quantity must be kept large enough. This is also an objective, but I cannot minimize this and maximize this one, so I select this as a constraint. Is that clear? Is that what the problem is with this kind of maximum and minimum problem? Okay, so let me minimize this linear function subject to this constraint. I build the Lagrange function. C is a variable, a parameter here. I build the Lagrange function and the computations are trivial. And the solution method is always the same. I don't want you to explain all the steps. You can just look at the slides. What I want you to understand is that the solution technique is always the same. Compute the derivatives of the Lagrange function with respect to the variables. They are here. Of course, the linear part becomes a constant in the derivative, while the square root part becomes something like lambda divided by square root of the variable, possibly times a constant, okay, like this. And these all must be equal to 0. And the strategy is always the same. Obtain lambda in each of these equations. If you obtain lambda from the first equation, lambda is equal to 2 square root of x1. But if you obtain this from the second, lambda is equal to square root of x2. From the third, lambda is equal to square root of x3. This means that this must be equal to this, and this must be equal to this one, okay? Clear? And then the constraint must hold. So how many equations do we have in this? Here we have 4 equations, which is okay, because remember that the number of equations that we have in the system is the number of variables plus the number of constraints, okay? So we have 3 variables, 1 constraint, 4 equations. Here, it is just written in a short form, but it is 4 equations. 1, 2, 3, 4. Now, how can I solve this? Of course, x1, square root of x2 is twice square root of x1. So here, square root of x2 is twice square root of x1. I replace, it becomes 4 square root of x1. Square root of x3 is 2 square root of x1 again. So I replace x3 with 2 square root of x1. Now this is an equation in x1, which means 1 plus 4 is 5, 7. 7 square root of x1 is equal to c. So x1 is equal to c squared over 49. Okay? It's very simple. Now, x1 is equal to c squared over 49. What about x2? x2 is twice this quantity. Square root of x2 is twice square root of x1. So x2 is 4 times this quantity, 4 times x1. So x2 is equal to 4 x star 1, 4 over 49 c squared, and lambda, which is the square root of x2, is equal to 2 over 7c, which is positive. Okay? Usually we found positive values for lambda in these kind of problems. Maybe I will be able to comment on this later. Just for the moment, just remember that lambda represents the derivative of the value function with respect to the budget. Okay, this is the main interpretation. Clear? How can I? Okay, now I obtain the solution using the first order condition. How can I be sure that my solution is in fact a constrained minimum point? Just using the general rule, the objective, not the objective function, this quantity at the left side of the constraint is a concave function of x1, x2, and x3. It's the sum of 3 separable, additively separable concave functions, okay? So this is a concave function. So C minus this is convex, okay? The objective here is linear then convex. The lambda is a positive quantity. So suppose that you have a positive quantity here. So this becomes convex and linear, which means convex. The Lagrange function with lambda replaced by the solution value for lambda is a convex function. Okay? So our unique stationary point is a minimum point. Clear? It is a global constraint minimum point for my function h of x. Now I want to show you another problem which is strictly related to this one. Just want to introduce this in this way. Suppose that you have another problem in which you don't have to minimize a function, but you have to maximize a function. The function that you have to maximize is this one at the left hand side of your current constraint. So you want to maximize this function. But you have a constraint, and the left side of the new constraint is your objective function, which your current objective function becomes your constraint in the other problem, and this must be kept equal to some value. Okay? This problem and this other problem that I have described in this way are strictly related to each other. So let me show you just in one example. I don't want to introduce duality theory, but I just want to show you this in one example. So our problem was minimize by choosing x And the function was x1 plus x2 plus 1/2 x3. This is h of x. Let me call this primal problem, so our starting problem, okay? And then I want to minimize this function subject to a linear constraint, which subject to a nonlinear constraint, square root of x1 plus 2 square root of x2 plus x3 equal to c. Now, suppose that I want to solve this problem that I already described in words. I want to maximize by choosing x. What was before this quantity? Remember that in fact when we have a problem with a constraint we have two objectives, okay? But one is kept in the form of a constraint. Now, this is a full objective, okay? We want to maximize this. Maximize by choosing x. This other function, which could be called g of x, which is equal to square root of x1 plus 2 square root of x2 plus square root of x3, subject to what was the previous objective function becomes the left-hand side of a constraint, x1 plus x2 plus 1/2 x3 is equal to a certain value, which is called, we can call this, I don't know, y, for instance. So this is called primal problem, and this is called dual problem, provided that, not generically in this way, but provided that this y is exactly equal to the minimized value of this function in this problem, okay? If this y is exactly equal to the minimized value of this function in this problem, and if c is exactly equal to the maximized objective function in this problem, then the two problems are strictly related and are called primal and dual, okay? That here, so let me write this. Provided that y is equal to h of x star. H of x star means the minimized, I find the solution which is called x star, I replace this, compute this quantity under this solution, and then if this is equal to the value at the right side of the constraint, and if c is equal to g of x star in the other. Okay? Clear? That in this case there is a strong connection between the two problems, and the strong connection is that the two problems have exactly the same solution. Okay? And then, if the two problems are in this strict relation with one another, then x star is the same for the two problems. Which is, if you think about it, it is a result that makes formally clear what I said before. I mean, we have two objectives. Here we want to minimize this one by keeping this to a certain level, because minimizing this is trivial, it's 0, 0, 0, okay? Here I want to maximize this quantity, which would imply increasing arbitrarily every variable, but I want to keep the sum of the variable basically at a given level, okay? It's clear that we have two objectives that are treated in different ways in the two problems. And if this there is this relation between the two, the solution is the same, because they are somewhat similar, somehow similar to one another. But of course, this condition must hold. Now I'm going to show you another problem which is similar to this one, which is it's dual basically. and it is a maximum problem. Okay, so it is an additional exercise. So this, if you go to the set of slides, review exercises on the first part of the course, so you see that we have here this problem, which comes at the end of the exercise, but this is a problem that we already solved here, okay? So maybe I should have called this, not the M. This is not Y, it is M, just to connect this with the other set of slides, M, and this is M. Just another way to call the constant, which is consistent with the other set of slides. Okay? So, this problem is the same we solve now, except that we called the constant C, okay? And now it is called Y bar. It is the same. So let me solve a problem which is the dual of this one, which is precisely this. Okay, so now my function is what was previously the constraint, and there is a linear constraint which was previously my objective function to be minimized. Now it is a constraint. It must be equal to m. Okay, let me solve this problem. The computations are exactly the same as before, very similar. Just because when I compute the Lagrange function, I have to compute the derivatives of the expression of the function and this, which are the same as in the previous problem, okay? So I have 1 over 2 square root of x1 minus lambda, 1 over square root of x2 minus lambda, 1 over 2 square root of x3 minus 1 half lambda equal to 0. Again, obtain lambda from the problem. Now lambda is 1. Now this quantity appears in the denominator, okay, you see? Lambda is 1 over 2 square root of x1, but also equal to this, but also equal to this. Similarly, this means that this is equal to this, which is equal to this. So square root of x2 is equal to 2 square root of x1, and square root of x3 is equal to 2 square root of x1. Then take these values, okay, and here, of course, lambda is equal to 1 over 1 of this, 1 over square root of x2. Now I have this constraint. What I can do now is to obtain both x2 and x3 in terms of x1 by just taking the squares here. x2 is equal to 4x1, x3 is equal to 4x1, replacing the linear constraint, okay? And I get, here it is 7. So x star 1 is equal to m over 7, which is x star 1 of m. X star 2 is equal to 4 times x star 1, so it is 4m over 7, and x star 3 is 4m over 7, and lambda is this one. Okay, now the exercise asks to build the value function. The value function is this one by replacing the optimal solution inside. The optimal solution is regarded as a function of m. This is why this is called value function. If I do that, that was left as an exercise. Please do this exercise. Just replace these quantities, x1, x2, and x3, into the function and obtain an expression that depends on m. The result is this red quantity. F star of m is equal to square root of 7m. Now, try to compute. This is also a way to check the results of your exercise, because if you compute the derivative with respect to m of this one, you should obtain, as a result, this quantity, okay? This is a way to check your results. Okay? So if I compute the derivative with respect to m, this becomes equal to this one. The derivative of this with respect to m is lambda star, is this. And this is a way to check your result. If your solution is correct, then the derivative of the objective function maximized, which becomes a function of m, and is called the value function, the derivative with respect to m should be equal to the value of the Lagrange multiplier at the solution, which is one of the most important envelope theorems, okay? Explained yesterday. Here there is an exercise to estimate the change in the maximized output using a linear approximation. Okay, let me do that. Suppose that we have in the exercise m equal to 14. How does the solution look like if the budget is 14? Remember, this problem is like maximizing the output subject to a cost constraint on the input factors, okay? If the solution is this one, it depends on m. If you replace 14, x1 becomes 2, x2 becomes 8, and lambda becomes 2 to the power minus 3 over 2. Okay? The value function becomes square root of 7 times m, which is 9.8995. Now assume that your budget changes from 14 to 17. And try to approximate linearly the change in the maximized output. This is easy because delta m, the change in m, is 3. The derivative of the maximized output with respect to m is just the value of the Lagrange multiplier, which at the level 14 is equal to this one. So it's just a matter of multiplying this, which is a derivative, times 3, which is an increment here. And this is a differential. So it is the linear approximation of a change, okay, of the function. If we multiply this, we get 1.06, okay? The true change would be 1.009, so this is not really good linearly as an approximation, but I mean, it gives the idea of the change. Also, I can approximate the percentage change of the maximized output by just dividing by f. The value of f star when m is equal to 14 is this one. I can approximate the percentage change, okay, by dividing by f star, okay? So divide this by this value and you obtain a 10.7% change of the maximized output. So basically, in this particular model, we can conclude that if we increase the budget by 3, which is more than 10%, because it was 14, it is increased by 3, it's 25%, okay? More than 25%. The maximized output increased by only 11%, okay? So these are side results that we can obtain from the solution to our problem and using linear approximations. But what I want to show you now is that here I've chosen an arbitrary m. What about having m which is exactly the minimized value of the objective function in the dual problem, okay? Okay, so this is the other problem in which I minimize subject to this constraint. If you take the solution to this problem and here you replace y bar with what? With the maximized value of the objective function in the other problem, which is square root of 7m found before. So you you replace this y bar with square root of 7m, you go into the solution, okay? In the previous exercise, this was called c squared, okay? You replace this, and you get exactly the same solution of the other problem. which is this one, okay? So if you take the solution to this problem, you replace to the constant here, what was, okay, this is a minimum problem, what was the maximized value of the objective function in its related problem, which was square root of 7m, you replace this here to y, you compute the solution and you obtain this one, and this one is exactly the optimal choice of x1, x2, and x3 in the other problem, which proves, okay, is this one, which proves that the two problems are strictly related to each other, okay? I mean, just regard these as two exercises. Don't worry about duality and dual problem and the primal problem. This is just a way to illustrate an important theoretical connection between different problems by means of examples. Just regard them as two exercises. Don't worry about if additionally you have some notion of what is a primal problem and its dual problem, and you have the solution to a problem, you can, for instance, solve a different exercise and you already know what the solution should be because you know this theoretical relation between the two, okay? So you can solve another problem and double check your result. Which here is a little time consuming because we have 3 variables, but in the 2 variable case would not be very time consuming. So it would be very easy to do. So primal problem, dual problem illustrated by means of 2 different examples. You have all in the slides. If you are interested, just look at here is another exercise in 2 variables that you can solve. So for instance, you have this problem. Maximize this utility subject to this budget constraint. I don't want you to solve, just solve it as an exercise. This utility is very simple, it's xy, subject to a linear budget constraint. Now consider this other problem. You don't want to maximize your satisfaction for a given budget. You choose a desired level of satisfaction, and you want that your satisfaction is this one, and you want to minimize the budget needed to reach it. This is related to the previous problem, okay? If your desired level of satisfaction is U bar, where U bar is exactly equal to your maximized utility in the previous problem, then the 2 problems have the same solution. Clear? Same solution means that the optimal values of x and y are the same in the 2 problems. Also, another property of this primality, duality, is that the optimal value of the Lagrange multiplier in one problem is the reciprocal to the optimal value of the Lagrange multiplier in the other problem, okay? So this is another relation between the 2. So it's, I mean, optimization has a lot of additional theoretical results which are important, and they all can be regarded as comparative statics of the solution, basically, which means sensitivity analysis of the solution, which means discussing the solution. How does the solution change if something changes, okay? How does the solution is in connection with the solution to other related problems? And all of this is called comparative statics of the solution. I didn't explain everything, but by examples I've shown to you that the meaning of the Lagrange multiplier in terms of derivative of the value function with respect to the budget. By examples, the connection between the problem and its dual. And all of this comes out from the fact that when you maximize something subject to a constraint, you have in fact 2 objectives. And in principle, you could minimize something else subject to another constraint. Okay, this is the connection between the 2 problems. And these are 2 examples of comparative statics. Okay, and another example of comparative statics is basically the it is broadly related to comparative statics, is also the implicit function theorem. Okay? The derivatives along a level curve is another example of comparative statics. Okay, so these are the basic topics. Now let me show you more examples on possible exercises for the examination. You should regard this set of slides as this set of slides plus the exercises on unconstrained and constrained optimization as very representative of the possible exercises in the exam, because what is really important is computing first partial derivatives, second partial derivatives, log derivatives, elasticities, linear approximations for two variable functions, unconstrained optimization, constrained optimization, derivatives along level curves. Okay, so the implicit function theorem exercises. And another example is the chain rule. The chain rule for two variable functions when you have a function of two variables, but both variables depend themselves on a unique variable. Okay, this type of chain rule. I have already uploaded another exercise, full exercise on this chain rule to the Virtuale this morning. So there is an additional exercise on the chain rule. One would be here, but we already saw this, I think, in one of the past lessons. It is this one. Let me see. Okay, we already solved this exercise. It is repeated here. We had a function of two variables, which was decreasing in the, this is a demand, which is decreasing in the price, but increasing in income. And you may have a model in which the price increases exponentially over time, and also the income increases, but linearly. It's supposed to increase linearly. So this is kind of scenario on the future evolution of the variables. And you want to track what the time derivative of this is and what the time growth rate is. The time derivative is d of t, is d prime of t, and the time growth rate is d dot over d. Okay? We solved this example already in another set of slides. It is repeated here. Remember, when you deal with this kind of multiplicative models, taking logs initially and computing this as the log derivative of d with respect to t is in general more convenient than computing d dot and then dividing by d. Computationally, it is more convenient to take logs initially because logs transform products into sums, and it is very easy to compute the derivatives of sums rather than products. Also, okay, so let me show you the examples here. First example, partial derivatives and elasticities of a function. This is the function. It is a function of x and y, but it has three factors, and each of them depends either on x or on y. If you take logs, you have the sum of three functions that are additively, it is additively separable in the three functions, okay? To compute the partial derivatives and the elasticities of this function and approximate linearly the function near this point, 1, 0, x0 equal to 1, y0 equal to 0. Okay, so partial derivatives. You have the product, partial derivative with respect to x. So 2 times square root of 1 plus y is a factor that doesn't affect the result. It will be the same in the derivative, but next we have to compute the derivative of a product, x squared times exponential of minus x. And the derivative is 2x times the exponential of minus x squared times the exponential of minus x. Remember the product rule for one variable functions. So this is the derivative basically inside the brackets is the derivative of a one variable function expressed as the product of two functions. Now there is a common factor here, And this common factor can be obtained because x exponential minus x is common to the two terms. So in the brackets, I only have 2 minus x. Now, if your exercise asks you to compute not only the partial derivatives, but also, for instance, the elasticities, since the elasticities imply dividing the partial derivatives by the function itself, it's often very useful to try to factor your result as far as possible, okay? As much as possible. In particular, try to obtain as common factors that are similar to the original function, because when you have to divide this quantity by the function, then you get immediately an easy result, okay? Okay, now the partial derivative with respect to y, now what is important is that this becomes as a multiplicative constant. So it is 2x squared exponential minus x times 1 over 2 square root of 1 plus y. So this is the final expression of the partial derivative with respect to y. If I want to compute now the elasticities of f, remember that I must start from the partial derivatives, divide each of them by the value of the function, which is this one, and then the partial elasticities are obtained by multiplying again, respectively, the result by x, and here the result by y. Okay, remember the formulas. Okay, so let's do that immediately. This was the derivative obtained in the previous step. X is because I multiplied by x in the denominator, and this is the function. Since we were very wise in solving this exercise on the derivatives, we already have a lot of factors that are common to both denominator and denominator, so we can simplify and we obtain 2 minus x as the elasticity. Usually, elasticities in multiplicative models have much simpler expressions than derivatives, okay? 2 minus x is the elasticity. Remember that it makes sense to compute this kind of elasticities for positive functions, okay? For positive functions. Because the elasticities are basically related to percentage changes, relative changes of the function times the level of the independent variable. So it makes sense to use these quantities for positive functions that change depending on another positive variable, as is common in economics. Partial elasticities with respect to y, sorry. The same, this was the result, multiplied by y, divided by the value of the function. Many common factors also here, this one and this one. Now, square root of 1 plus y times square root of 1 plus y becomes 1 plus y. Okay, so this is the result. Again, very simple. Now, an alternative way to compute elasticities is to take logs. One could even start from the elasticities by taking logs, computing elasticities, and then going back to the derivatives. Okay, let me compute the elasticities by taking logs. The elasticities can be regarded as the logarithmic derivatives of this function with respect to the two variables, each multiplied by the corresponding independent variable. Okay, so this is the expression, an alternative expression for the elasticity with respect to x and with respect to y. Taking logs means having sums. The log of the function is this one. The derivative of the log of the function, or the logarithmic derivative of the function, is 2 over x minus 1. If I multiply by x, it's 2 minus x, which is the previous result. The same with y. The derivative with respect to y of this is this one. I multiply by y, and I have the previous result, which is y divided by 2, 1 plus y. Now, suppose that you start just want to, to make a suggestion. Suppose that you start from the elasticities. So you take logs and you compute the elasticities without computing the derivatives. How would you go back to the derivatives starting from the elasticities? Well, this is the partial elasticity with respect to x. Very easy. Compute it by taking logs. But the exercise also requires to compute the partial derivative with respect to x. In order to obtain the elasticity, starting from the derivative, you should have divided by the function multiplied by x. Multiply by the function and divide by x. Okay? If you multiply by the function, which is this one, and divide by x, you obtain the partial derivative. Do that by exercise. So sometimes it can be useful to start from the elasticities and go back to the partial derivatives. For instance, in this case, suppose that you have this one variable function. Just to let you know how important it is to having clear in your mind what are the relations between these measures of change. Suppose that you have this function of one variable, f of x is equal to x squared times exponential minus 1/2 x times the log of 1 plus x times 1 over square root of x plus 1. 4 factors. Okay, if you use the product rule to compute the derivative, do you know how to use the product rule for a function which is made up of 4 factors? No worries, just consider them as 2 functions. One is this, one is this. Okay, so you have 2 factors, you can apply the product rule, okay? But for each of them, you have to apply, this is nested into the previous method, you have to apply the product rule, right? So it's not very easy to compute the derivative of this. But if your problem is to compute the elasticity with respect to x of f, first of all, you take logs, not partial derivative, this is a one variable function, so this is just a derivative. Okay, so this is the elasticity, right? So take the log of f of x. The log of f of x is equal to log of x squared, 2 log of x, okay? Plus the log of the exponential of minus 1/2 x, minus 1/2 x, right? Which is plus the log of this, plus the log of 1 plus x, okay? That would be, okay, that was a bad choice. Anyway, it works. Okay? You switch to logs. Products between functions is the sum of the logs of all the functions. So you have this. And this is square root of x plus 1 in the denominator, x plus 1 to the power of minus 1/2, okay? So it is minus 1/2 log of x plus 1. Is that okay? And this is the log of f of x. Now, the derivative with respect to x, or already the elasticity, I can compute the elasticity already, which is x, that multiplies the derivative of this with respect to x, okay? And the derivative of this with respect to x is 2 over x for the first term, minus 1/2, okay? What is the derivative of this one? Is 1 over the log of 1 plus x, log of something, 1 over something times the derivative, okay, of the argument. So 1 over the log of 1 plus x times the derivative of the argument. right? That true? Minus 1 over 2 x plus 1. Is that true? So this is the elasticity, okay? Now, when you have the elasticity, if you have the elasticity, which is easy to compute, is easier than computing first the derivative of this one, you can go back to the derivative, because in order to obtain the elasticity, remember that the elasticity is also equal to f prime of x over f of x times x, okay? Now you have this, which is this one. So in order to, and this is the elasticity, in order to obtain the derivative, just divide by x and multiply by f of x, okay? So you should take this one, divide by x, remove this x, and multiply by this quantity, which is f of x, okay? This is the derivative. Of course, this is an arbitrarily complicated example, but in principle, if these connections are clear to you, this simplifies a lot of things in some cases, and also gives you a way to double check the results, always. This is the importance of knowing the theory behind the exercises. Means knowing the connection between different solution methods, which is really, really important, okay? Okay, forget about this example, this was only to show you the importance of this. Now, this was just to say that if you compute these elasticities, then you can go back to the derivative. So you can even start from the elasticities and then go back to the derivatives, and then double check your derivatives by computing the derivatives, for instance. So you have many ways to do that. Now, the linear approximation of our function at the point 1, 0, near the point 1, 0, remember that the linear approximation to a function near a point is the value of the function, this is a two-variable function, the value of the function at the point times the gradient at the point. Gradient is the row vector of the partial derivatives at the point times the column vector of the deviations, okay? X minus x0, y minus y0. Here are the computations, the value of the function at the point. Remember that the function was this one. So I replace here to x1 and to y0, and I obtain that. The value of the function at the point is this one, is 2 over e. The partial derivative with respect to x evaluated at the point is again 2 over e. Just replace the numbers into the expression obtained before. The partial derivative with respect to y is 1 over e. So I can approximate the value of the function in this way. F at the point 2 over e plus gradient means partial derivative with respect to x times the deviation in x, which is x minus 1, plus derivative with respect to y times the deviation in y, which is y minus 0. So something can be simplified here, and you get 1 over e times 2x plus y. So this is the linear approximation of our function, two-variable function, near a point. Suppose that I ask you also to use this linear approximation to approximate linearly f of 1.3, 0.4. Our initial point was 1, 0. Now it is 1.3, 0.4. X has increased by 0.3, y has increased by 0.4, okay? So I can use and compare the results with the true value. So the linear approximation, using the linear approximation, and using, remember that the linear approximation is expressed in terms of x and y, so here are the two values. Replace the two values into the formula for the plane, basically. It is a plane, a linear approximation. You get this, okay? So the value of the function is this one, while the true value, computed using the formula, is 1 0.09. So this is 1.10, and this is 1.09, which is pretty close, okay? And this is a linear approximation. This is an exercise on unconstrained maximization. Okay, in which the function is a little more complicated than the ones seen before. First of all, this is not an additively separable function in x and y. Okay, this part depends only on x, plus a part that depends only on y, but this is a square root of a sum, and this is not linearly separable in the two functions, okay? Because it is a nonlinear transformation of a linear function, so it is not additively separable. Remember that don't always try to exploit the values that you obtain for aggregate quantities into the solution of the system. Don't always try to use the, step-by-step solution method in which you obtain a variable and then you replace the variable in the other equation. Look at the structures before using this standard method. First, look at the structures, because there may be better methods. If you compute the derivatives, the partial derivatives, this is unconstrained, so we don't need any Lagrange function here, okay? We want to find the stationary point and possibly later check that this stationary point is actually a maximum point, which means, for instance, that this function is concave. So, derivative with respect to x is 1 over 2 square root of this quantity minus 1 over 4. And this must be equal to 0. Partial derivative with respect to y is again 1 over, it would be 2 in the denominator and 2 in the numerator, because this is a composite function, okay? But the 2 in the numerator and denominator can be simplified with each other. We get this minus 2 over 5y, and this must be equal to 0. So don't try to obtain x or y from this one. Just look at this. You have already the numerical value of this aggregate square root quantity that appears also here, okay? So obtain from the first equation this 1 plus x plus 2y square root of is equal to 2. Sorry, I mean, don't worry if I recommend not to obtain one variable in terms of the other, because this is a very common mistake that I see in these cases. If you do that, so in principle you should be able to solve the exercise, but the computations become very complicated, and it's very easy to make mistakes. And also another point is not just before of the exercise and the performance of the examination, is becoming able to identify structures into these quantities, okay? Why is that? Why do we have a common quantity in the two partial derivatives? Because here we have a power function, and when you take derivatives of power functions, these derivatives can be expressed in terms of the power functions themselves, okay? Very often. And the same happens for exponential functions. Okay, so it's clear that you have a common part here in the partial derivatives, because this is also a composite function. So the first step of the differentiation is the same for the two partial derivatives. This doesn't mean just knowing tricks. This means knowing the theory. Okay, so this is really important. Now this quantity is equal to 2. So replace 2 here in the other equation. It becomes 1/2 equal to 2 over 5y. So 5 is just equal to 5 over 4, and since 5 is equal to 5, y is equal to 5 over 4, then you can go back to this equation, replace here to y its value, and you get x. Because then you replace here, you take the square of both sides, and x will be equal to 1/2. Here. Okay. Now, is this actually the unconstrained maximum? Can you see this? 5 over 4. Okay? So it becomes 1 plus x plus 2 times 5 over 4. This becomes 5 over 2. If you remove the square root here, you get 4 here. Then x is equal to 4 minus 2.5 minus 1, so it's 0.5. Here. Is that true? Is that really a maximum point? Look at the functions. 3 additive pieces. If we can prove that each one is concave, then this is the sum of concave functions. This is linear, independent of the sign. Linear means concave. This is concave, square root of... why is it a concave? Remember the criteria that I gave you. Concave transformation of a linear function. It is concave. 1/5y squared would be a convex function of y. So it's negative, it's concave. So all 3 functions are concave. This is concave. The unique, if you find a unique stationary point, this is a global maximum point. So this is the solution to our exercise. A very similar exercise, I don't comment on this exercise. This is very similar because square root of 1 plus x plus 2y is in principle very similar to this quantity, the log of 1 plus x plus 2y. I should add plus 1 here, basically, and I would have 2 very similar functions, okay? Anyway, it is a very similar exercise in structure, because when you take the derivative of the log, you have the same quantity here, okay? So follow the same steps and solve this exercise. I don't comment on this exercise, it is in the slides. It is an exercise similar to this one. Here is the solution, okay? Don't replace, don't obtain x or y in one equation and then replace in the other. Just exploit the fact that you have the same quantity here, and the value of this quantity is 5. Very common structures in applied problems. Okay. This is a constraint. Maybe let me see if we have many more exercises. Okay. So maybe we could take a break now, okay, 15 minutes break, and then continue with the summary exercise. Okay, let's take a break.
Maybe it's a stupid question, but...
Not stupid, no questions are stupid.
Can you use x and epsilon, you are in the epsilon instead of x1 and x2? Because can that be confusing?
Yeah, sorry, I couldn't understand. What about replacing the names of the variables?
Yeah. Instead of x1 and x2.
So you want me to redo the exercise with x1 and x2? No, I mean you can call the variables anyway. So what is the problem? Is the name of the variables?
Yeah, when we use x1 and x2, can get quite confusing sometimes.
You can get?
Confusing. The name of the x1 and x2 we should be setting up x.
No. I must use x1 and x2 because if you have 3 variables, okay, you can add z. If you have 4 variables, you can add w, but then it becomes quite strange. Okay, so in principle, any textbook in which the 2 variable case is the one I used to teach many concepts, but in principle, also the 3 variables, 4 variables, 10 variables case is important. In that case, the variables are indexed with 1, 2, 3. Okay, so you need to become familiar with the general notation. Okay, you also need to become familiar. I use both of them. Just to let you become familiar with alternative possible notations. Okay, let's take a break. 15 minutes, and then we start again with the second part. Sì.
Ho capito, questa è una funzione affine, giusto?
1 più x più 2y è una funzione affine.
Quindi sarebbe g di x, la funzione interna sarebbe questa qua.
Sì.
Questa qui è lineare, come
Questa è lineare.
Non ho capito questa qua.
Allora, un quinto y quadro è la parabola fatta così.
Ah, ok, quindi
Se lei chiama, si ricordi che y è solo il nome di una delle due variabili, la può chiamare x se vuole. Se lei avesse una funzione di una variabile che è un quinto x quadro,
sarebbe una
è una parabola fatta così, quella è convessa. Se col meno davanti, la negativa di una convessa è la definizione di una
Ok, grazie, ero perso.
Prego, no problem. Let me start again. Can you hear me? Everything should be okay now. Okay, let me start again with another example. This is an example. Okay, so far we have studied examples in which basically we had a linear constraint or a linear objective function, but this is an example, nothing difficult, nothing difficult compared to our previous examples, but qualitatively different, in which we have a constraint maximum to be found with a nonlinear function and a nonlinear constraint, okay? And this is, again, something which is based on a tangency condition, so nothing changes from the viewpoint of our first-order conditions. We will show that the Lagrange function is a concave one, so no problems. The only thing that changes is the graphical representation. So we have a constraint, the red line here, which is nonlinear. Okay, so it is maximizing xy subject to 1/2 x squared plus y equal to b. Why is the constraint nonlinear? Because if you make the constraint explicit in terms of y, you get y is equal to b minus 1/2 x squared, okay? So this is a parabola, okay, like this, a concave parabola, and the top is at the point 0 where the value is b, of course. Y is equal to b minus 1/2 x squared, okay? When x is equal to 0, y is equal to b, and of course it will have an intersection with the x-axis somewhere here. While the level curves of our objective function are equilateral hyperbolas, so y is equal to 1 over x. Y is equal to constant over x, like this. The larger the value of k here, the outer is the level curve. By the way, I want to show you, yesterday I've shown to you that the analytical conditions on the Lagrangian can be rewritten as the tangency condition between the constraint curve and one of the level curves of the objective function. This necessarily, okay, this was implicit, this is an analytical argument, okay? But there is also a graphical argument by which the tangency condition must hold. Suppose that you have, this is a very typical situation, a nonlinear constraint like the previous one, for instance, like this, no? Okay, no, this is not. This is a nonlinear constraint, only one curve. And then we have the indifference curves, or the level curves of our objective function. And we have to maximize this, okay? So we have something like this, and we have to maximize. Okay? Suppose that u of xy equal to c, okay? In the direction as c grows, the larger the level of utility that we consider, the outer is our indifference curve, okay? Now this is the budget constraint or something similar. Why is the solution necessarily at the tangency? Because remember that you have to maximize u of xy subject, or f of xy, subject to g of xy equal to b, okay, which is our budget constraint. This is the budget. The maximum cannot be on this, for instance, on this level curve. Why? Because if by increasing the level of our objective function, we get more and more external level curves. The maximum cannot be here, because if I remain on the constraint, on the black line, so with the constraint always being satisfied, I can move in this direction and cross level curves with higher and higher level. So I am improving my utility. Conversely, it cannot be here, because if I move, remember that I can only move on the black line, okay? Because the constraint must be always satisfied. If I move in this direction, I cross level curves of higher and higher level. And clearly, the highest value compatible with the constraint will be on the tangent level curves, because the second level curves do not satisfy this property. Is that clear? This is the geometric argument for the tangency condition. And if it is not at the tangency, this cannot be the optimum, because I can move along the constraint and cross higher level curves. This is basically the argument. But of course, this argument on the tangency is just a way, the tangency between this curve and the black one is only a way to summarize the two conditions in the Lagrange function, okay, by rewriting differently the quantities that appear there. So there is an analytical reason behind this tangency, and also an intuitive geometric argument. Okay, so suppose that you want to maximize this, build the Lagrange function. First observe that, okay, this is a good point. This is not concave. 1/2 x squared plus y is a convex function of x and y. With the minus sign, it is concave. So this is concave. We will find a positive value for lambda here. So this piece will be concave. Unfortunately, this is not concave. How can we be sure that what we find is the maximum? Wait a moment, and you will discover. This is the Lagrange function. I build the necessary conditions. Okay, so take derivatives. Derivative with respect to x is y. Minus lambda minus lambda x. Okay, minus lambda x equal to 0. The derivative with respect to y is x minus lambda equal to 0, and then we have the constraint. Okay, from the first equation, so here I get lambda equal to x. And since lambda is equal to x, I get here y is equal to x squared, okay? And then I have to satisfy the constraint where y is equal to x squared, so I replace x squared here. It becomes 3 over 2x squared equal to b. X is the square root of 2b over 3. Y is this squared, so it is 2b over 3. And lambda is equal to x. Okay, so there is a unique point. For instance, if b is equal to 6, this is a numerical value to our solution, okay? And f of x star y star, if I replace 2 and 4, becomes equal to 8, for instance, okay? This is a numerical example. But this is an important remark here. The Lagrange function with lambda positive, remember that lambda is positive in our solution, okay? It is positive. This is a positive quantity. Makes this part concave, but unfortunately, this part is not concave. How can we be sure that this is the optimal solution? This is a good point, and it has also an easy solution. The first argument, provided that you have a function which is easy to represent graphically in two variables, the first argument is that clearly this point that represents a solution is at the tangency between the constraint curve and the highest level curve of our objective function. And this is strictly related to the fact that despite this is not concave, the level curves of this function have the usual shape, okay? They are hyperbolas like this. They are decreasing and convex. Whenever you have level curves, this is a geometric argument for the two variable case. Whenever you have level curves that are decreasing and convex like this, and you have a constraint curve which is linear or concave like this, clearly you have a tangency point, okay? So you have a tangency point, and this is clearly a maximum in this case. But what is the analytical point by which we can be sure that this is a constrained maximum? Because remember what I tried to explain to you a couple of, maybe last week. Maximizing a function implies finding the values of x and y by which this function reaches its highest value. If instead of having this function, I have an increasing, strictly increasing transformation of this function to be maximized, okay? The values that maximize the new function will be the same. And this is one of the most important practical tools in optimization. I mean, if you want to maximize, we can try with one variable functions as a simple example. Suppose that you want to maximize two x minus 1/3 x squared, okay? This is a parabola this is a parabola with concavity, downward concavity, okay? If you want to find the maximum, you compute the first derivative, becomes 2 minus 2/3 x, okay? And you set this equal to 0, and you get that x is equal to 3, basically, okay? Here, this is the global maximum point of this function. This is a concave function. If you have an increasing transformation to this one, an increasing transformation is, for instance, the exponential of something, okay? So if you have the exponential of 2x minus 1/3 x squared, okay? This is an increasing transformation of our previous function. The value that maximizes this function is again x equal to 3. Why? The reason is very intuitive. If you select x equal to 3 here, you get the highest possible value for this quantity. Okay? Now this quantity becomes the exponent of an increasing transformation. Okay? The larger the exponent, the larger the result. This is the highest possible exponent is when x is equal to 3. So the highest possible value of this function, which is e to that exponent, is again x equal to 3. Is that clear? So whenever you take an increasing transformation of a function, you get a function which is maximized by the same values by which the original function was maximized. Right? Another example could be for instance, taking logs or taking any other increasing transformation, okay? Clear? Now, go back to this exercise. This is not concave. Is there any way to make the problem, the issue is this part. Is there any way to make this function concave by modifying this part in such a way that this is an increasing transformation of xy, but such that the new function here becomes concave? Because here we are maximizing a function subject to a constraint. Don't worry about the constraint. This just restricts the possible choices, our choices, okay? But we want to maximize this function, which is the same as maximizing an increasing transformation of this function. Is there any increasing transformation of this such that this becomes concave so that we can conclude that our function is concave here? For instance, if I raise, the point is that this is a Cobb-Douglas function and the sum of the exponents is 2. In order to have a concave function, the sum of the exponents must be less than 1. Just raise this to the power of 1/3, which is an increasing transformation. The cubic root of something is an increasing transformation. Okay, so right here, x to the power of 1/3 times y to the power of 1/3. And the values that maximize this are the same that maximize the new function. So this is, all of these considerations are written here. Maximizing this subject to this constraint, of course you don't have to change the constraint. The constraint is the same. It only restricts your possible choice of the variables. But clearly, if your choice maximizes this subject to the constraint, it maximizes also this one, the cubic root of the original quantity, okay? In case B, the Lagrangian is concave because xy to the power of 1/3 is concave. So in this case, we have our standard case in which our Lagrange function is concave. So basically, we cannot conclude that this problem has a concave Lagrangian when we replace to lambda its value, but we can conclude that the equivalent problem, which is this one, has a concave Lagrangian. And the equivalent problem has the same solution to the original problem. Okay? So this is a way to extend to other cases all of these properties. It's enough that you take an increasing transformation of your function such that your function has the desired properties. Of course, equivalent means that the values of x and y are the same. Also, this subject to this constraint will be maximized by x equal to 2 and y equal to 4. You can check this by exercise. But of course, the value of the function at the solution will be different, okay? Here, I have to replace x star y star here, and here I have to replace x star y star here. And also the value of the Lagrange multiplier will, in general, be different. But the solution in terms of x and y will be the same. Okay, so this is, and by exercise, you are invited to solve this problem and to check that the solution is the same as this one. Now, about the original problem, compute a value function at the optimal solution. So the solution was this. So replacing the function was just the product of x and y, replace this times this, okay? And it becomes 2b over 3 to the power of 3 over 2. Compute the derivative with respect to b. This is 3 over 2 times 2b over 3 to the power of 1/2 times 2/3. And what we get is this quantity, which is precisely the optimal value of lambda at the solution. Okay, so this is a way to double check your result. Another question related to this, this type of exercise could be this one. Write the equation of the level curve of f through the point x star y star, where x star y star is the optimal solution. So basically, we want to write the equation of this level curve, the one that passes through the optimal solution point. Okay? And show or check that its slope at x star y star is equal to the slope of the budget constraint at the same point, which is basically checking the tangency condition that must hold at the optimal solution. In order to do that, assume b equal to 6. In some cases, it is easy to do that for any b. In this particular case, assume b equal to 6. Okay, so what is the level curve through x star y star? The level curve through the optimal solution point is one where the function is constantly at the same level that is reached at this point, okay? So it is xy is equal to this number, where this number is f of x star y star. So it is the value of the function at the optimal solution. If you replace x equal to 2, y equal to 4, you get 8, okay? So this equation is xy equal to 8. What is its slope at the point xy? Of course, this is a trivial exercise. You could just make y explicitly in terms of x, y will be equal to 8 over x, okay? But anyway, let's use the implicit function, differentiation theorem. Just compute the ratio between the two derivatives with respect to x and with respect to y. It is minus y over x. You must evaluate this at the point where x is equal to 2 and y is equal to 4, okay? Okay, so it becomes 4 divided by 2, it is minus 2. What is the slope of the budget constraint curve at the same point? The budget constraint can be made explicit, but it could also be computed implicitly. It can be made explicit, we did that before, okay? Y is equal to b minus 1 over 2x squared, where b is equal to 6. Compute the slope at the point of abscissa 2. Okay, so the derivative is minus x. At the point of abscissa 2, it is minus 2. Okay, so the slope of the constraint curve is equal to the slope of the indifference, the level curve passing through the optimal solution point. There is, of course, another way to compute this, because I can rely on the implicit representation of the constraint, which is an implicit function. It can be made explicit, but it is implicit here. So it was, let me see, 1/2 x squared plus y equal to b. So g of xy was 1/2 x squared plus y, okay? So the partial derivative with respect to x is equal to what? 1/2 times 2x, okay? So is equal to x. The partial derivative with respect to y is equal to 1. So the derivative of y with respect to x along this curve, which is the constraint curve, using the implicit function theorem, is minus x divided by 1. At the point where x, it must be computed at the point 2, 4, okay? When x is equal to 2 and y is equal to 4, in particular y doesn't appear here, it is equal to minus 2. So we get the same result also using the implicit function theorem, okay? By the way, the result doesn't depend on b, which is the constant term of the constraint. That clear? Okay, this is another example. So this is basically the solution. Okay, this is about first and second order approximation of a two-variable function. Okay, I mean, it's again based on the derivatives of the Cobb-Douglas function, so it is very simple. Just have a look at the second order approximation. This will not be part of the written examination, but focus on the first order approximation, okay? For completeness, you also have the second order approximations, but I suggest you to look at the function, compute the partial derivatives, by exercise compute also the second partial derivative, because this could be a question. Computing second partial derivatives could be a question in the exam, and then just compute this part, which is a linear approximation, okay? It is all displayed here. You don't need to. This was the other exercise on the chain rules, but this is done already. This is a problem on unconstrained, but let me see how many things we have here. This is a problem of unconstrained optimization with additively separable functions, so I leave you as an exercise. It's all worked out, it's very simple. This is a companion exercise very similar to the previous one. But I want to go, I want to focus on this last exercise here. Okay. Suppose that you have this function, f of xy is 100 minus x minus 5 squared minus y minus 4 squared. And I want to solve a problem of unconstrained maximization to this, okay? Unconstrained, without constraints. Clearly, before doing every computation, just look at the function. This is a constant which is 100, minus something which can only reduce the total value below 100 because it is a square, so you subtract something which is positive or zero. This is positive or zero, this is positive or zero, and you are going to subtract these quantities. If you want to maximize this function, what is most convenient to you is to subtract these quantities when these quantities are zero, okay? Because then you preserve your value 100 here, which will be the maximum of your function. Clear? Clearly, the maximum will be at the point x equal to 5, y equal to 4, because only at this point these quantities are zero, otherwise they are positive, and so you preserve your value, which is 100, which will be the maximum of the function. So just look at the function sometimes before doing the computation. Let's obtain the same result by using the analytical techniques. Gradient equal to 0. Don't expand the squares here. Minus 2 times x minus 5 equal to 0 is the partial derivative with respect to x. And minus 2y minus 4 equal to 0, this is the partial derivative with respect to y. Solution, x equal to 5, y equal to 4, okay? Is that the maximum? We already discovered that this is the maximum because it cannot be in any different way. But of course, this is convex. This is convex. With the minus sign, they become concave. Okay, so this is a maximum. Now, this is the interesting point. This is unconstrained maximization. Now, suppose that you want to, here we could select any possible values of x and y. In particular, it turns out that the optimal values are 5, 4. But suppose that now we have a constraint. You cannot select any possible values for x and y, but only those values by which this sum, x plus 2y, is equal to c, where c is a number larger than 3. So for instance, this one, if c is equal to, I don't know, 6, this is not good for our constraint problem, okay? Because it doesn't satisfy the constraint. Okay. We try to understand more about the solution to this problem in connection to the solution of the unconstrained problem by looking at the level curves of our objective function. Okay? So f of xy equal to a given level. If f of xy must be equal to k, we work out this, and this is x minus 5 squared plus y minus 4 squared equal to 100 minus k, okay? This is the level curves at 8k. In the representation of the constraint is just y is equal to minus 1/2 x plus c over 2, okay? Where c is the constant term of the constraint, which is the budget, let's say, which is regarded as parametric here. There may be different situations. First of all, let me represent the level curves of the two variable functions. And these level curves are circles, okay? This is the equation of a circle, which is centered at the point 5, 4. It has a radius which is equal to basically the square root of this quantity, okay? And we know, okay, what are these circles? Are like this, okay? They have all the same center and different radius, basically. And clearly, we discovered already that the maximum is at the point 5,4. So if you move across these circles, the directions of growth are the red arrows, converging towards the center point, the center, where there is a maximum point for that particular two variable functions, okay? It's clear, it's like this. If you take sections, you have circles of smaller and smaller size. Now, what happens with the constraint optimization problem? You want to maximize this quantity, okay? It depends on where the constraint lies. If it is like this, because the constraint has this general equation, the larger is C, the more external is this blue line, okay? Because it is the intercept, okay? Can you see that? So the solution will drastically change depending on whether your constraint is, for instance, here, or whether your constraint is here. Okay? It will change because, of course, you cannot move to this point, but you have to stay. You have to stay on this blue line. Okay? So let me solve the problem with the constraint using the Lagrange method. If you solve the problem using the Lagrange method, you have this, which is the objective function, plus lambda times c minus x minus 2y. Okay, so what is important here is that just try to form some intuition about, you will find a solution. The solution will be characterized by the tangency condition, okay? But what do you expect if your constraint is here, for instance, and the optimal solution will be this one? What do you expect about the value of lambda, the Lagrange multiplier, at the solution? So far we found positive values in many examples, okay? Will it be positive or will it be negative? Remember, what is lambda? It is the optimal value, the sensitivity of the optimal value of the maximized objective depending on the C quantity, okay? So depending basically on the intercept here. Here the direction of growth are toward the center. If your constraint lies below the center of the circle and you increase C, you move your straight line upwards, you improve your solution. You improve the value of, because you move to higher level curves, okay? But what happens here, if you increase, if C is such that your constraint is here, okay, and you increase C, so you move the constraint to a more external position, do you improve your solution or do you worsen your solution? You worsen your solution, okay? Why? Because if you have to stay here, then the solution will be here. But if your straight line is like this, you will be on a lower level curve of your objective function. So you will diminish the value of the maximized function. You should expect that basically if your C is such that the straight line lies below the center, the lambda at the solution is positive. But if it lies above, the lambda at the solution will be negative, because the lambda signals how your solution, optimized solution, changes if you increase C. But here, if you increase C, you go to a region where it is not possible to reach the previous levels of the objective function. So you worsen the level of the objective function at your solution. If you solve the example, and this is an important point, because if you solve the example by using the Lagrange technique, which is a standard problem, so you have your constraint, which is linear, okay, okay, this you compute the partial derivatives, now they include lambda, you obtain lambda from the first and the second equation. You can obtain minus lambda, and minus lambda is equal to 2 times x minus 5, or from the second equation it is equal to y minus 4. This means that this must be equal to this, the usual technique. Y is equal to 2x minus 6. Then you replace y into this constraint equation and you get a linear equation in x. And you solve your problem and you get x is equal to c plus 12 divided by 5, and y is equal to 2c minus 3 divided by 5, and lambda is equal to 2 13 minus c divided by 5. This means that lambda is positive if c is less than 13, but lambda becomes negative if c is larger than 13, okay? And it becomes 0 when c is equal to 13. What is the meaning in terms of geometric terms? When c is equal to 13, this is a straight line, you can just check these computations. When c is equal to 13, you have a straight line that passes exactly through the center. This is the meaning of lambda is 0. It is indifferent. If you marginally move the value of c, you have a change of the maximized value of the objective function, which is negligible. Lambda is 0, okay? That's because we are already at the unconstrained maximum, because this would be the unconstrained maximum. But if we are below here, or above here, the constraint matters, in the sense that it brings the solution away from the optimal solution of the unconstrained problem, okay? In particular, here, we get a solution in which lambda is positive, because if we increase c, starting from this point, we improve our solution in terms of maximized value of the objective function. But if we start here with c large enough, and we increase c again, then we then our maximized function diminishes, okay, with the new c. And this is the reason why it is one of the reasons why lambda and the sign of lambda is important to assess the sensitivity of the solution with respect to changes in one parameter, okay, which is parameter c in our problem. Also, if you want to look at this example again, this is not part of the program, but there is an additional slide here. And in this additional slide, I want to show you that what we learned in this example is related to more general problems in which we don't have the equality constraint. We have an inequality constraint. X plus 2y must be less or equal to c, okay? Less or equal to c. If you go back here, this means that you have to maximize the function with these level curves, but you don't have to stay strictly on the straight line that represents the constraint. You must remain below, okay? Below or on the straight line. So this is a wider problem. If it's intuitive that if the straight line will be like this, so c less than 13, qualitatively, it's not optimal to stay below. You would go to the straight line, and the optimal solution will be there. We say that the constraint is binding in this case, okay? But what about this case? Suppose that your constraint is here. You have to maximize the function by remaining below the constraint. And now the constraint is here. Is it optimal to move your solution to the constraint? No, because you already have here the unconstrained maximum. So the highest possible value that this function can take on, okay? So it's not optimal to move to the constraint. It's optimal to remain here. So you have two cases here. One in which it is optimal to move to the straight line that represents the boundary of the region of choice. And another case, where the constraint is here, in which it is not optimal to move there. It is optimal to remain in the inner region of choice, okay? Okay, this is, so we would like a more general technique that allows us to write down some conditions such that this comes out as a solution. And this can be done by the so-called They are called Kuhn-Tucker conditions, conditions for maximum problems or minimum problems with inequality constraints that are in which we build a Lagrange function, but the conditions are somehow different compared to the ones that we use in with equality constraints. Okay, this is not part of the program, but this is just to let you know that there exist more general settings in which we have inequality constraints, and this example shows that an important property of these problems with inequality constraints is that in some cases the solution is when the constraint is binding. So similar to equality constraints, okay? So here, for instance, that this quantity must be less or equal to C doesn't matter, because at the optimal solution it will be equal to C. But here it matters, because at the optimal solution is strictly less than C. So there are solutions in which the constraint is binding, solution in which the constraint is not binding, so it is slack, we say, okay? And all of these solutions globally can be derived using the so-called Kuhn-Tucker conditions that are a more general set of conditions than the usual conditions of the Lagrange function, okay, that we have with equality constraints. This is just to let you know that there exists this more general setup. You may hear about Kuhn-Tucker conditions. You may see that in these Kuhn-Tucker conditions, there are coupled conditions like this. The Lagrange multiplier must be non-negative, but the product between the Lagrange multiplier and the resource, the amount of the resource which is left, must be zero. If you look at this condition, this means that either this is satisfied when either the Lagrange multiplier is zero or the constraint is satisfied as an equality, okay? So there is a way to group together all of these considerations that we made naively about the previous exercise, okay? And these are called Kuhn-Tucker conditions. The last exercise here is already the one that I've seen already about the dual problem. So there is no more examples here. Okay, this is basically what is required for the written examination of the midterm of the first part. So if you have questions, I will put, okay, I remember, I will put a couple of, I will put the midterm examination of last year and 2 years ago as an example. But I guess you can already find them in last year's material already. And I will put the updated instructions for the online examination. I received an email. We will have a room. So I will also let you know what is the room for people who want to take the examination at the university. It is one of the labs. For instance, should be there. It should be the blue lab room. It is on November 5 from 3 p.m. to 5 p.m. Okay? Should be the blue lab. I will put the announcement also in when it is confirmed. I will put the announcement in the virtuale, in the informations in the virtuale. Questions? Everything okay? Very easy. The first part is very easy. First part is really easy. For most of you, it's already known material, apart from some extensions. The second part will be on dynamic integrals regarded in a dynamic perspective, mainly, and dynamics. So it will be maybe fresh, a new part for most of you. And also something more about matrices. All matrices and computations about matrices will be part of the second. Because what we learned here is only the basic tools for notation to understand. But the larger part on matrices will be on the second part, okay? So that will be part of the program of the final examination, the second midterm. Good. Have a nice day. Per? This is a very delicate point because it comes in the middle of a lot of different. I'm really busy, so I will try. I will do my best, but you should not expect to have your results in 1 week, basically. I will do my best to give you my results in 2 weeks, just because I have a lot of other commitments in that period. And then teaching starts again, so I have to concentrate all of them during the break, because then teaching starts again. So, why this question? Because it is well known that I take a lot of time to... Okay, I will do my best. Okay, thank you. Bye. Could you please repeat why if the budget line is below the max? No. If the budget line, If the budget line, Simone Menghi, the question was by Simone Menghi. If the budget line is above, the maximum, and C increases, then you move the budget line on a position which is higher than the previous one. So you go, your tangency point with the lower level curve, okay? So this is the reason why F worsens. Instead, if you are below the unconstrained max and you increase C, you move towards a higher level curve. So your objective function improves. This is the reason. Okay? But I mean, in this particular problem, in which the maximum is here and you have circles around the maximum corresponding to lower and lower levels of your objective function. Okay. Thank you. Bye.
Pero